Swayam Prabha. Digital India. Educated India.
Welcome back everyone, and in this module we will be discussing on the topic of continuum mechanics. The first three modules will be on the first part, namely continuum mechanics restricted to one dimensional, and in the next three modules we will be looking at the higher dimensions, 2 and 3 dimensions of this topic. So the topic of today's discussion is continuum mechanics. And we will start our discussion in one dimension. For this is going to continue for the next three modules. And to begin with, we will primarily spend a bit of time on the motion with respect to what frame we are talking about. So essentially, we will be focusing our attention on the frames of reference. And there are essentially two frames. One is the so-called the material frame, or this is also the moving frame, or the body fitted frame, or it is a more popular word of this material frame is the so-called Lagrangian frame. So I think with all these nomenclature, it is quite easy to conclude what sort of frame we are talking about. This is a frame which is moving with the body, and typically in this frame we are able to know how far a particle has traveled, including their position and velocity. So particle typically in flow or motion knows how far they have traveled their position and velocity. How far they have traveled their position and velocity. Okay, so then the next the next frame is the so-called spatial or the fixed frame, or the so-called Eulerian frame of reference. And we are talking about an observer. In this frame of reference, the observer is on the fixed frame. They will know the particle's position, their velocity, but not their origin or how far they have traveled. So an observer on the fixed frame will know the particle's position, velocity, but not its origin, or how far it has traveled. Okay. So let us now dive a little bit deeper into these frames of reference. The first frame we are talking about is the material coordinate. And we are, in this case, we are looking at a cross section which is moving with time. So in material coordinate, again, we are talking about particle moving in 1D. So let us say at t equal to 0, we have a particle which is moving in 1D, and it is at a cross section along the x-axis, and in the material coordinate, the coordinate also moves with the particle. So at any given point of time, the coordinate has moved to a new position, capital X, and what we expect is that, so let me write what I am just trying to highlight. So at t equal to 0, we have the cross section located at x equal to capital X. So this is our capital X. So x equal to capital X, and this is my reference configuration, right? And at a later time, so at a later time, let's say t greater than 0, the cross section has moved to x equal to some chi, right? So let's say this is at t equal to 0 and this is at t equal to some t, which is, this is t greater than 0. So the position has now changed to chi, and now this small x chi is a function of the initial position and it's a function of time. So this is the position at t equal to 0, the initial position and the function of time. Okay, so we can rest be assured that that for consistency we have that chi at time t equal to 0 is x. So that's the initial condition. So then our coordinate, we are going to assign our coordinate capital X comma t as our material coordinate. Remember, we are only talking in 1D, one dimension. So material coordinate, or this is the so-called Lagrangian coordinate, right? So the displacement with respect to the original position, is u of x comma t is given by chi of x comma t minus x. So this is my displacement of the particle at any given point of time. We can see that the displacement is 0 at t equal to 0. So then so what I just said is the displacement at t equal to 0 is going to be x minus x, which is 0. Okay, so then of course we can also define the velocity. The velocity v of x, capital X comma t, is going to be partial u partial t. Okay, so then so that is what the description of the motion is in material coordinate or moving coordinate or the Lagrangian frame. So then in spatial coordinate, we could again define a similar set of variables. For example, the displacement. This time I am going to represent all the spatial coordinate variables with small letters. So my displacement now is small u, which is x comma t, and velocity is v of x comma t. And for fixed x and non-zero velocity, for fixed x and non-zero velocity, the cross section at x, keeps changing. So this is what is the description in a fixed frame of reference, right? So the cross section is changing. Okay, so then so we can compare it with material coordinate. We can compare this description in the material coordinate. We see that in material frame, in material coordinate, we have that the fixed x, we follow a particular cross section. So in the moving coordinate for fixed x, we are going to follow a given cross section. So that cross section is not going to change with time. So we follow a particular cross section while in spatial coordinate the location is changing, right? So while in spatial coordinate, it turns out that the location is changing. Okay, so since the two coordinates must give the same values at a given point of time, we must have the following relation holding true. So since the two coordinates must give the same value, we have that u of x comma t is u small u of chi of t, right? So the displacement in the Lagrangian frame must be the displacement in the Eulerian frame, and similarly v of x comma t is small v of chi comma t, where chi is again a function of x comma t, right? So these are all functions of x comma t. So now what we have is that x is chi of x comma t, and so what we have now is that u at x comma t, u at small x comma t. So chi at capital X comma t is small x. So we have this relation. So u at x small x comma t is going to be capital U at chi comma t, and similarly v at x small x comma t is v at capital V at chi comma t. So if we were to change our variables from the Lagrangian frame to the Eulerian frame, we use this left hand side set of relations, and if we have to use from the Eulerian to the Lagrangian frame, we use the right hand side of the relationships. Okay, so let us look at, it might seem a little bit confusing to begin with. So let us now focus and look at one example to understand this whole set of ideas better. So we have the example as follows. So a cross section starting at x equal to 3 is located at x equal to 7 at t equal to 2. So in the material coordinate, we would like to see what is the displacement. So in the material coordinate, we see that so the starting location is x equal to 3. So for the starting location, whether you use the material or the the spatial coordinate, will be the same. So capital X equal to 3. This is, and we have a displacement. We need to find the displacement at t equal to 2, and so the displacement u in the material coordinate is 7 minus 3, which is 4. Or what we have is that u at initial condition x equal to 3 and time point t equal to 2 is going to be 4, which is the displacement. Or the relation between the chi of 3 comma 0, the initial condition is 3, right? So that's my initial position, and chi at 3 comma 2, that is at time point 2, is 7. So 7, which is also u at 3 comma 2, which is the displacement, plus the initial condition, which is so this is 4 and the initial condition is 3. Okay, so this simple example helps us to identify how we are calculating the variables in the various coordinates. Okay, so then if we look at the same idea in the spatial coordinate, we see that at at t equal to 2, the displacement of the cross section at x equal to 7 is 4, right? So the displacement at x equal to 7 is 4, and so I have that small u at 7 comma 2, right? So small u at 7 comma 2 is 4. So this is my Eulerian displacement. Okay, so that is how it is. So then now let us this particular example was relatively simple. Let us look at slightly more complicated example where the difference is clearly visible between the two coordinate systems. So the second example I have is suppose a bar deforms in a way that the cross section moves according to chi equal to x of 1 plus 2t divided by 1 plus t. Okay, so then if we were to find in material coordinate, so again in material coordinate, if we were to find the displacement u of x comma t, this is going to be chi minus x, capital X, where capital X is chi at t equal to 0, right? So this is going to be x of 1 plus 2t by 1 plus t minus x, and we get that this is also equal to tx by 1 plus t. Okay, so we have just used this formula that we are given, and so this is my displacement in the material frame. So then we can check that the velocity in the material frame is partial u partial t, and this is going to be the derivative of this u, this capital U is going to be x over 1 plus t square. Let us now do the same exercise in the Eulerian frame. So in the Eulerian frame, we have that small u is going to be the displacement, which is the capital U at x equal to we have the formula that chi is x times 1 plus 2t divided by 1 plus t. So I can get that capital X is nothing but 1 plus t times 1 plus 2t of chi, or this chi is at any given time point chi is small x, right? So then what I have is we evaluate this u, we evaluate the u. So my u is, from the previous slide I found that u was t capital X by 1 plus t. So instead of capital X, we are going to use this quantity. Capital X is this quantity. So u is t capital X by 1 plus t. So my capital X now is 1 plus t divided by 1 plus 2t times small x, and now I have the final answer as tx by 1 plus 2t. So that is my displacement in the fixed frame of reference. And then if we were to find the velocity in the fixed frame of reference, again this has to be the velocity in the material frame evaluated at x equal to 1 plus t by 1 plus 2t times small x. And again if we again plug the relation for the velocity, we see that this is also equal to x by 1 plus 2t times 1 plus t. Most important to see is that this value is not equal to the velocity in the material frame. So this is the material frame we are talking about, and this is the fixed frame or the Eulerian frame we are talking about. So essentially we see that there is a difference in the velocities when calculated in either of the two frames, right? So that difference is going to motivate us to find certain relations in both the moving and the fixed frame of reference, the relations of the continuum of objects. So what we have is the domains where the displacement and the velocity also change are different in both coordinates, Okay, so if we were to calculate the domain of the bar in the Lagrangian frame, domain of the bar in the Lagrangian frame, we have that the domain lies between 0 to L naught, right? And suppose we were to find the same domain of the bar in Eulerian frame, then in the Eulerian frame it the distance or the length will vary from u at 0 comma t to u at L naught comma t. So u is the displacement, so we have to add the initial coordinate, that is L naught. Okay, so to highlight this whole idea, suppose we were talking going back to the previous example. So what I'm saying is referring to example 1, the previous example, we see that u my small x, my domain length is u of 0 comma t plus to u of 3 comma t plus 3, right? So that's the domain initial coordinate of the domain. And then I see that x, u at 0 comma t was 0, and u at 3 comma t is 3t by 1 plus t plus 3. So this is my example 2. So that's the example we are talking. We just finished a few minutes back. So we see that x lies between this range to this range. Okay, so that is how the domain length might vary when we are looking at the various frames of reference, comparing the two frames of reference. Now I just want to my first task at hand now is to derive certain certain models governing the dynamics of these continuum objects in both frames of reference. So to do that, let us start with some basic notation. So the notation, I'm going to adopt the notation of the partial derivatives denoted by ux. So we have ux is partial u partial x, and this is sometimes also known as partial x u, right? And similarly, if we have uxx or partial u partial x square, or we have partial 2x partial x2u, these are all identical. Similarly, if we have u of x comma t, or partial u partial x partial t, or we have partial x partial t of u, right? So all these are equivalent. So these are my notation for partial derivatives. Okay, so now let us now again look at the material derivative of a function. So material derivative. So derivative in the material coordinate. So suppose I have a function f of t, f which is a function of capital X comma t. Capital X is a length coordinate in the material frame. So this is a function in material coordinate, and this is also equal to small f of x comma t. This is in spatial coordinate, or what we have is capital X of capital F of x comma t is f of capital f of chi of x comma t. So the two functions are related to each other, the capital F and small f, as follows, with the arguments being replaced as shown in this slide. So then, if we were to find the time derivative of the function capital F, right, the function in the material coordinate, we see that this is also equal to, so this small f is f of x comma t, because chi is small x, right? So small x is a variable in the Eulerian frame or the spatial coordinates. So now capital F, capital T is going to have two variables, small x and small t. So now we are going to rewrite this derivative of the capital F function in small f. So this is partial f partial x times partial x, partial chi partial t. So this is the case, plus partial f partial t, and this is also equal to partial f partial x times v of x comma t plus partial f partial t. So what we have now is that we are now going to rewrite, I am going to denote this derivative, the time derivative of capital F, as, so this is my material time derivative. So I am going to denote this material derivative with a capital D notation. So capital D dt of f has been found to be partial f partial t plus v times partial f partial x. So where this partial f partial t, these are all the spatial derivative, or the regular derivative we are quite aware of, the spatial derivative or the time instantaneous derivative. Okay, so this is the relation I wanted to highlight here, or the so-called the relation for the material derivative, right? Notice that on the left hand side we have the Lagrangian derivative or the material derivative, and on this right hand side we have this time derivative or the so-called Eulerian derivative or the spatial derivative, which is the instantaneous derivative in the spatial coordinate or the instantaneous time derivative. Okay, so then, so what we see is, suppose instead of capital F we look at one specific function, let's say velocity. We substitute capital F to be our velocity v. So what we have is, so in particular what we see is v is du dt, which is u of t plus v times u of x. That is the relation that we just saw. And then from here I see that my small v is nothing but ut by 1 minus ux, right? Or my v, certainly v is not partial u partial t, or which is ut. So v is related to ut as follows. So this is the relation. So this is the material velocity in the material coordinate, right? And we see that it is related to the instantaneous displacement as ut plus v times ux. Okay, so similarly, so again using this idea in example 2. So going back to example 2, we see that ux is t divided by 1 plus 2t. And from here we see that ut is x by 1 plus 2t square, and we see that v is x divided by 1 plus t times 1 plus 2t. So this is the same. So this is what it is. So we have just used the formula above, the time, the material derivative, and we are getting the relation that we had just seen when we were solving example 2. So same. So this is the same as in example 2 that we found, right? So essentially we have found a relation between the velocity in the material frame and the velocity in the spatial frame or Eulerian frame. So let me now tabulate the results. So results. So let me write down the results in both coordinates. So on one side we have the material coordinate, and on the other side we have the spatial coordinate. Spatial coordinate. So what we have is that, so partial f partial t, and on the other side we have partial f partial t plus v times partial f partial x. And similarly we will have partial f partial x, and on the other side we have this, so the derivative partial f partial x is going to be 1 over 1 minus ux times partial small f partial small x, right? We can just check what we did, that is, see, this partial in the material coordinate is actually capital D. So this is our capital df dx. We can, this second example we have just seen how we got the result above, right? And then similarly if we have 1 by 1 plus ux times partial f partial x, again this is the material derivative, and this is equivalent to partial f partial x. So this is the Eulerian derivative. And then finally if we have a derivative of the form partial f partial t minus v over 1 plus ux f of x, this is going to be partial f partial t, right? We can just look at one example. We can the example we have already seen here just few minutes back. So these are the various types of transformations we can use from one frame to the other. So then this is what first part of our development of the model in continuum mechanics, namely determining the material and the spatial derivative of any function. Then the next part that we have to focus is on certain mathematical tools or certain results which will allow us to eventually write down the model, which is essentially the form of a conservation principle, right? Again, we have seen in classical mechanics some conservation principles like conservation of momentum, conservation of energy. Here to begin with we will use conservation of mass. Again, we are not talking about the results in relativistic theory. This is purely classical theory, classical mechanics, where the mass is conserved. So I think I am all out of time for this particular module, and in the next module we will start our next part of the analysis, namely by introducing the mathematical tools which will allow us to eventually derive the model for the continuum of these objects. Thank you so far for listening.